All right, hello everybody and welcome to the final video of the second module of the class. Today we're going to be discussing how price and quantity instruments can both be used to deal with environmental externalities or specifically in this case, help mitigate the effects of pollution. So we're going to start off this class by discussing different ways of categorizing pollution before moving on to discussing what the cost of pollution would be and thinking about how we can most cost effectively implement policies for managing pollution and mitigating those effects. Then we're going to move on to really the meat of the lecture, which is thinking about quantity-based policy instruments instead of the Pigouvian taxes, which we've been considering in the past. Okay, so in addition to the more obvious way of categorizing differences in pollution by where they occur or what part of the environment they affect, such as thinking of air pollution, water pollution, or soil pollution, we can also think about different types of pollution according to what extent they exist in the ambient environment over a period of time. And so when we have pollutants for which the environment has little or no absorptive capacity, we consider those stock pollutants. And so those pollutants accumulate in the environment until they are removed externally. And so you can think about pollutants which have a long half-life in terms of how long it takes them to biodegrade, such as plastics, heavy metals, or synthetic chemicals. We could also think of fund pollutants, not fun pollutants, for which the environment has some absorptive capacity, such as carbon dioxide, which, yes, is accumulating in the atmosphere at faster rates than which the Earth can absorb it. The environment can absorb it, but naturally there is some degree of carbon dioxide absorption, as well as organic waste, which is going to decompose over a quicker time horizon. And so it's important to note here that some pollutants can be stock pollutants at one level and fund pollutants at another, such as carbon dioxide, for example, maybe thinking about it locally as being absorbed and doesn't really impact the local environment, but when we think about its impact on the global environment, it becomes a stock pollutant in that the absorptive capacity is exceeded. So just be aware that the zone of influence is going to matter when we categorize pollutants as being stock or fund pollutants. And we'll continue to use this terminology throughout the rest of this video. And so we're going to look at a series of graphs today. And I think it's going to be easy to get confused as we jump from one type of graph to another, is largely they're going to have the same kind of shape of having two axes with a cross on them, with an X on them, with an upward sloping curve and a downward sloping curve intersecting. But the axes and the labels for these curves are going to change. So I want to make sure that we're really clear about what these curves are representing. So there's going to be two main types of costs associated with pollution. There's going to be the cost from the damages caused by the pollution. So might have this illustrated as marginal damage costs. And there's going to be the costs of pollution control itself. And so this may be labeled with MAC or marginal abatement costs. And so one of these is the cost of pollution. The other one is the cost of controlling the pollution. And though we're going to illustrate these curves linearly, we're typically going to be illustrating the marginal curves. And so when we illustrate a marginal curve increasing, this is going to suggest that the marginal damage of the curves, the marginal damage of pollution are going to increase as more pollution is emitted into the environment. And you can think about this as relating to that fund pollutant categorization of pollution, of if there's a limited capacity, maybe not fund, but the stock, either one, if there's a limit to the capacity of the environment to absorb that pollution, then the first couple units of pollution which we emit are going to be absorbed, and the damage is going to be minimal. And so the marginal damage, the marginal cost of that pollution is going to be small. However, as we pollute more, then we're going to be exceeding that absorptive capacity, and the marginal damage of each additional unit is going to increase. Similarly, we can also think about the marginal abatement costs increasing as we try to limit pollution. Once again, this hopefully is somewhat intuitive. With the first unit of abatement, the first effort to clean up any pollution is going to be more efficient than the last, taking out the very last bit of pollution. So if you think about having a whole bunch of fish in a barrel, right? So we've got a rain barrel, we've got a whole bunch of fish in there, and we want to scoop some of the fish out. And if we dip a net in, we pull it out, we don't really have to search around for those fish for the very first couple of fish we take out. The marginal cost of the very first fish we take out is going to be relatively low. However, once we're down to only like 1 or 2 fish left, then we've got to really look inside the barrel, try to time up where the fish is swimming and pull it out. And so that's kind of the same issue here with pollution, where it's going to take more effort to extract that very last little bit of pollution from the environment than the first. They're probably going to have a transition point between those two, or any effort of removing pollution between the very first unit and the very last unit is going to fall somewhere in between the two in terms of cost. So if we think of the marginal damage, the marginal cost from each additional unit of pollution as increasing, then if we have zero pollution on the left hand in the origin of this graph, and we have, say, full pollution, I'm not sure what that would be, on the right hand side, then we would have an upward sloping marginal damage curve. And so the marginal damage from the first unit of pollution would only be this much, but the marginal damage, not the cumulative damage, the marginal damage of this much pollution would be this much. So the per unit cost of the damage increases, and the per unit cost of abatement of pollution control is going to increase as well. However, remember, we discussed this in one of the earlier videos. If we have pollution moving in one direction on the graph, we have abatement moving in the other. So full pollution equals zero abatement, and zero pollution equals full abatement. So we have fully reduced all pollution into the environment. And looking at that graph, we would start at the right-hand corner, the lower right-hand corner, and we could show that as we abate more, the cost of reducing pollution per unit of pollution will increase. And so when we set up the graphs this way, we can see that there is a optimal level of pollution and an optimal level of abatement where these graphs, where these curves cross. And that gives us this optimal level of pollution at E star. And so this reinforces a point from a couple weeks ago, I think maybe last week, no, it would be from the video right before the first exam, where we thought about the optimal efficient level of pollution not being zero. And that is largely in part because there is a cost to reducing pollution. And when that, when the marginal cost of pollution control exceeds the marginal benefit from pollution reduction, which is essentially just the foregone damages, the avoided damages, then it's going to be inefficient to abate beyond that point, and we could use that cost for enhancing education or healthcare, something else that we care about in the country. And so we could also use this graph to illustrate what would happen if technology would make abatement cheaper. In other words, if it would lower the marginal abatement cost. And so once again, at zero abatement, the per unit cost of abating is going to be zero because we're not abating anything. But let's just say that, let's say that it looks like this. So we'll call that MAC2. Well, now the optimal level of abatement is going to be where the marginal damage curve intersects marginal abatement cost 2, which is going to give us a new E star, call that E2. And as abatement is running right to left, that means that the optimal level of abatement is going to be greater, the optimal level of pollution is going to be less. And so by increasing the efficiency and the technology by which we can reduce pollution in the environment, we're going to reduce the optimal amount of pollution in the environment. Now, this optimal point is just telling us what would be best for society, what would be the most efficient level of pollution for all of society. It's not telling us what would be the actual level of pollution or abatement if the firms were left to their own devices, if the private companies were to choose what would be their profit maximizing level of abatement. And so, just to think about how much they would actually abate if there was no government intervention, would they choose to have that optimal level of pollution, or would they abate more than the optimal amount or less than the optimal amount? And the answer here, as you could probably guess, is B. They would choose not to abate at all because that doesn't impact their profit maximizing production decisions. That is an externality that's imposed upon the rest of society. And so it's going to be the goal of policymakers to adjust the incentives of firms which pollute to internalize the cost of that externality and to make them incorporate that into their profit maximization decisions. Okay, so as we transition from that graph to a new graph, let's just make sure that we're aware of how the terminology that we're going to use is going to change as well. So the marginal abatement cost is going to be the same. We're going to think of the marginal cost of reducing pollution by 1 unit as increasing the more pollution we reduce. Remember, it's getting harder to find that one fish in the barrel. And the marginal benefit of abatement is going to be directly tied to the marginal damage of pollution. And so if we are reducing that first unit of pollution, so if there's full pollution, whatever that may be, that last unit of pollution has a large marginal damage, right? So you can rewind the video, go back and take a look. And because we thought of the marginal damage curve as increasing, then that last unit of pollution is going to have a large cost, a large marginal damage associated with it. So if we reduce that very last unit of pollution and we produce 1 unit of abatement, so now there's 1 pollution reduction unit that's produced by the companies, that's going to have a lot of benefit. So the marginal benefit of abatement is going to be directly tied to the marginal damage of pollution. It's going to be the benefit received from avoiding 1 more unit of pollution. And similar to actually, I mean, the exact opposite of that marginal damage of pollution, because abatement is the inverse of pollution. These are going to decrease as we reduce pollution. So if we have an almost perfectly clean environment and we take out 1 unit, the very last unit of pollution, there's only that 1 unit of pollution in the environment, then the benefit's not going to be that great, right? So the marginal benefit of that isn't going to be that helpful. It's much more valuable to start taking out pollution when we have an already dirty environment. So we'll illustrate how this will work in a new graph here. But it's basically just going to give us the exact same answer as thinking about the marginal abatement cost and marginal damage cost, though when we present the graph this way, present the information this way, we get more of a traditional supply and demand type presentation of the information, where we have upward sloping marginal cost curve, downward sloping marginal benefit curve, and we have a demand for abatement and a supply of abatement, more or less. And so this is then going to give us that optimal point of the efficient level of abatement, the official level of pollution, where the marginal benefits from abatement are equal to the marginal costs. And importantly here, the goal of, or not the goal, but the efficiency promised by that optimal level of abatement isn't going to be maximizing the total benefits. If we wanted to maximize the total benefits, then we would fully abate. There would be no pollution in the environment. What we're concerned about is that cost efficiency of pollution abatement, so that we have enough resources to spend on other contributing factors to human happiness, and in which case we have to take into account the marginal costs. And so the total benefits from abatement are all the area underneath the marginal benefit curve. The total costs are all the areas underneath the marginal cost curve. And so the net benefits are going to be the total benefits minus the cost, and that's going to be maximized at the equilibrium, where we can subtract this red triangle from that green area, and we create the green triangle that looks like traditional consumer surplus and producer surplus. And as promised, green triangle. So by now we've seen a couple examples about how we can have the most efficient solution when we make decisions on the margin. We set the marginal benefit equal to the marginal cost, and really that was the first equimarginal principle that we considered in this class. Now, the second equimarginal principle is going to be when we think about minimizing pollution when there are multiple polluters. And here we're going to focus on the marginal cost again. And when we have multiple polluters that are multiple firms or companies or individuals who are polluting the same type of pollutant, then we can most efficiently achieve a desired level of reduction in emissions when we set the marginal costs of pollution reduction equal for all polluters. And so this runs, I think, contrary to what the intuition may be, that if there are two firms which are each polluting 10 units apiece, and we want to cut pollution in half, then we tell both of those firms they can only pollute 5 units. That's not going to be the most cost-efficient way of cutting pollution in half if those firms have different marginal abatement costs. So, for example, we may see firm 1 having a lower marginal abatement cost than firm 2. And by putting these, both the marginal abatement cost curves of the firms on the same graph, but setting the axes and running in opposite directions of each other, then we can find the point at which those marginal abatement curves cross, and we can also find all combinations of points at which the marginal costs of abatement are equal. And if we have a desired level of pollution reduction, then we can find what combination of points on each of these graphs that have the same price would add up to equal the desired level of pollution reduction. So we're going to look at some numerical examples of this later in the class today, but I wanted to at least make you aware of what the second equimarginal principle is, which is once again focusing on marginal conditions to promise economic efficiency through pollution reduction. Now, the second equimarginal principle is a textbook solution. So theoretically, that's going to promise efficiency. But we also know that the real world doesn't behave like a textbook, in that there are criticisms of using such a technocratic way to address this problem along the lines of it being hard to generate knowledge about the cost of abatement for individual firms, where there can be such heterogeneity across firms and industries when it comes to the marginal cost of abatement, and they may have an incentive to lie about what their cost of abatement is. And so there's actually been environmental economic studies of the degree of honesty when it comes to abatement by firms. And so there are alternatives to these if we feel like these are legitimate concerns. We can have emission standards, which are more of just a command and control type approach. We can place taxes or fees on emission to at least have some sort of market connection. And we can create transferable emission permits, which may provide a more incentive compatible way for firms to be honest about what their emission standards would be, because otherwise they would then be facing higher costs. And so we'll discuss that more later in this class. Now, when we have non-uniformly mixed fund pollutants, then total emission is not the sole concern. We are not only interested in the sum of the pollutants from multiple firms, but also the distribution, and specifically as it relates to the difference from emissions to concentrations of those pollutants on various sites that we may care about where it's absorbed. And so different locations will have different environment capacities for absorbing pollution, and more pollution may then make it into population centers in areas where that capacity is surpassed. And so we can think about a series here of examples of non-uniformly mixed fund pollutants where not only what we're concerned with is that total amount of these pollutants, but also where they accumulate and which firms or which polluters are going to not only emit the most, but have the greatest impacts on society. So there are a couple of key terms here which are important to understand, one of which we've already discussed in this class, but first we can think of ambient standards, which are legal ceilings placed on the concentration levels of specified pollutants in the air, soil, and water. And so not necessarily how much is emitted, but on how that emission has turned into concentrations in the ambient environment. The receptor site is going to be where that concentration is measured, and the emission comes from the point of pollution. And the transfer coefficient is going to be how we think about transitioning from emission at the point of pollution to concentrations at the receptor site. And it's going to just be, as the name suggests, a coefficient indicating to what extent or to what degree the pollution is reduced from the emission site to the receptor site. And so the second equimarginal principle still applies here, but we're no longer thinking about the marginal cost of abatement of emissions, but we're thinking about the marginal cost of concentration reductions. And we're going to look at a numerical example on the following slide to see how we can think about this. But basically, we're just going to calculate the marginal cost of concentration by dividing the marginal cost of emission by the transfer coefficient. And so, as you can see in this image down here, if there is absorptive capacity along the stream, moving from, as pollutants move from left to right and being measured at receptor site R, then a greater amount of emissions from site C will reach the receptor site than the amount of emissions from site D. So we could think of B and A maybe as having uniformly mixed fund pollutants, as an equal amount of pollution from both of those sites would maybe reach site R, receptor site R. But the concentrations of the pollutant at site R received from site C are going to be greater than the concentrations of pollution at site R received from site D, even if they both pollute the same level of emissions. So let's think of just a simple example here where we just have one single receptor, as in the previous example with receptor R. And so there will be two firms with the same marginal cost of emission reduction, and the transfer coefficient for firm 1 is going to just be 1, and it's going to be 0.5 for firm 2. And so if we want to reduce the concentration of the pollutants at the receptor site by 5 units, how are we going to go about reducing or allocating that reduction between firm 1 and firm 2? And we're going to think about doing so in a cost-efficient manner, which is going to minimize the total cost among both firms. And so looking at a table where we can compare emission reduction, concentration reduction, the marginal cost of emission reduction, and the marginal cost of concentration reduction, we can see how we could implement or visualize the second equimarginal principle. In the second equimarginal principle with a non-uniformly mixed fund pollutant, when there are different transfer coefficients between the polluting firms, is going to come not when the marginal costs of emission are equal, but when the marginal costs of concentration reduction are equal. And so we can then find, we know that in this column, for both firms, there's going to be combinations of emission unit reductions which are going to have the same number of, the same value for the marginal cost of concentration reduction. For example, it costs the same amount to the marginal cost of concentration reduction is going to be 6 for the 6th unit of emission reduced for firm 1. It's also going to be 6 for the 3rd emission unit reduced for firm 2. So we know we want to allocate pollution reduction according to when those marginal costs are equal, but we also want the total concentration reduction to equal 5. So what combination of concentration units reduced is going to equal 5 and have the same marginal costs? Well, if we set the marginal costs, if we're looking at what the total amount of concentration reduction would be when the marginal cost equals 6 for both firms, then we have reduced 6 units from firm 1, and we've reduced 1.5 from firm 2, so that's too much. What about when the marginal cost of concentration reduction is 4? Well, then we would have reduced 4 units of pollution from firm 1, and we would have reduced 1 unit of pollution from firm 2. 4 plus 1 equals 5. We got it. So that would be the most cost-effective way to minimize, to take out 5 units of pollution, 5 concentration units from this environment. And we could find that by setting the marginal costs equal to each other and finding the combination of units reduced, which would give us our desired number of units reduced. And so this is how we would accomplish this in the a non-uniformly mixed fund pollutant with a single receptor. So when there are many receptors, the equimarginal rule will still hold. We can still do the math and be able to calculate it. However, this is usually pretty complex and it's difficult to implement in practice. So we're not going to consider examples like that in this class. So now that we have an idea of how the second equimarginal principle could work both in theory and with some simple numerical examples, let's consider the price versus quantity approach to reducing pollution in the environment. So the first quantity-based instrument which we're going to consider for pollution reduction is that of command and control. And so command and control is just going to be a way of targeting the desired quantity of pollution which is produced and regulating either the amount of that pollution or the production which leads to that pollution. And we can do this through a variety of methods. We can set an emission standard, which would legally require the amount of pollutants that an individual source, individual firm or economic agent can emit to fall below a certain level. Or we could require technology standards such as adopting scrubbers or smokestacks or anything which would reduce that pollution. But the main point here is that this is going to be kind of a heavy-handed government approach that may not leave as much room for economic efficiency, but is going to strictly enforce certain standards to be met that we would want to use in cases of extreme environmental damage, when an action or a pollution would have incredibly high marginal damages, which we can't leave up to the free market or market-based incentives to be able to regulate on their own. So when there is a significantly high externality. And a common example of this is going to be DDT. And I love teaching this part in class because I like to ask if anybody else watches Monday Night Raw or some WWE and watches them get the DDT finishing move. So I think this is going to probably make this video last a lot longer to upload if I play this over too much. But this is the DDT finishing move from professional wrestling. So the real DDT is not a wrestling move. It was a pesticide which was used in the US in the mid-20th century. There was limited capacity of the natural environment to absorb it before it would make its way into the surrounding environment and impact other life forms in the environment. And though it was popular for being effective as a pesticide, it harmed birds, human health, specifically peregrine falcons, bald eagles, and it made their shells be really brittle and break, and actually almost led to, it did lead to several species of birds making the endangered species list, coming dangerously close to extinction. And Rachel Carson wrote about it in one of the most famous pieces of environmental literature, being Silent Spring in 1962. And it was eventually, as this became more popular and kind of brought to the forefront of the attention of the American public, was banned by the EPA in 1973. So there was a command and control policy established that set the quantity of the pollutant that could be used, or the product that could be used, to zero. It's still used in Africa as a last resort to fight malaria, but given the extreme cost of malaria, this could be an economically efficient way of making a trade-off between environmental damage and human health if we have this instrumental value of nature. So while it has a way of, well, these command and control policies may be necessary to limit some of the extreme externalities in the environment, there are problems with it. So first of all, unless we are taking that kind of zero threshold approach, setting the ambient standard to zero, then there are high information costs, and monitoring is not easy. So if we're requiring firms to only emit 20 tons of nitrous oxide per year, I don't know if that's a lot or not, then monitoring that is going to be a cost-intensive measure on its own, and maybe wasteful to measure, and obviously there's an incentive for firms to not be truthful about how much they emit. Secondly, we have to know what that optimal level is, in which case we need information about marginal cost, marginal benefits, and command and control is only concerned about the cost and not about the benefits. And so this requires, once again, much more information about the impact of that externality on society. And it's not going to be efficient if firms have different abatement costs. And by not allowing them to engage in trade between each other when it comes to abatement and pollution control, is going to possibly disregard efficiency gains, which could be attributed to the trade of pollution control between firms, while not changing the desired amount of pollution, or not having a difference in the level of pollution in the environment compared to what could be achieved by creating a tradable permit system. And so this is also going to ignore heterogeneity and the impact of the command and control policy to different types of firms. And it may be harder for smaller firms who aren't able to innovate or have access to other sort of technologies to create a substitute for that polluting good. But perhaps most importantly is that when there's a command and control policy, it creates no incentive for firms to innovate if they can reach the set limits. So if that limit isn't zero and we just say you have to reduce your pollution by 50%, reduce your emission by 50%, okay, firms may innovate up to that point, but then once they reach that 50%, then there's no incentive for them to innovate further to further reduce their pollution. Whereas if we place a marginal tax or a marginal cost on each unit of pollution or each emission, then there's an incentive to invest in greener technology or less dirty methods of producing their output. So when we only think about quantity-based instruments which don't take into account price, then these are going to be various forms of command and control type policies. And we're going to have less efficient solutions than if we would take more of a price-based instrument, which may take the form of a Pigouvian fee or tax or subsidy, which would be a way of compensating or accounting for an externality, or it may incorporate quantity-based instruments into the market framework and allow for a set standard to be traded between firms according to their different costs of abatement. So the easiest example to think of when it comes to price-based instruments for pollution control is just that of the Pigouvian tax or subsidy, which we discussed last week. So if we think of production as being directly tied to pollution, and we know that there's a defined relationship between pollution and production of a good, such as with our steel industry example, then we can set the a tax equal to a negative externality or a subsidy equal to the value of a positive externality as a way to correct for that externality and bring the market back into its socially desirable equilibrium. Now, when we place a tax directly on emissions instead of on the product, then the firm can have a choice about how much it chooses to emit and how much it chooses to abate, how much of its pollution it chooses to reduce, and between how much it's going to pay in taxes while continuing to pollute. And so, as you can guess, an efficient solution here for the firm is going to come on the margin. It's going to come from the intersection of its marginal abatement cost curve as well as the marginal benefit of abatement reduction, which is not paying the tax. So once again, thinking of the horizontal axis here as measuring pollution abatement from left to right. So this point 0 here actually means that there's full pollution. 10 is going to be full abatement. And thinking about what the efficient level, how much that firm would choose to abate given a tax at price T, we're going to think about their marginal decision making. So for those first couple of units of abatement, going from 0 abatement to 1 unit of abatement, 2 units of abatement, the marginal cost of abatement is going to be less than the tax. And so if they wanted to, in this case, pollute 9 units, which would be abating 1 unit, then it would make sense to not pollute those full 9 units and choose instead to abate 1 unit more and only pollute 8 units. So they'd be faced with that same decision with their 8th unit of pollution, and they would recognize that it's still going to be cheaper for them to abate 1 more unit of pollution. And now we're starting to get closer in the difference between the value of the tax and the value of abatement until we reach point A star. And point A star would fall at 4 units of abatement or 6 units of pollution. After that point in time, if the firm says should we abate a 5th unit, should we further reduce our emission? Well, now it's actually more costly to do that than to just pay the tax. So they're going to continue to pollute. They're not going to abate any more than 4 units. And we can then determine what would be their profit maximizing, what would be their optimal level of pollution reduction based on where the value of the tax intersects the marginal abatement cost curve. So when we think about how much revenue is generated by the tax, we want to keep in mind that tax revenue is going to equal the per unit value of the tax multiplied by the taxable quantity. And so when there is no abatement and we just have a tax on the amount of pollution and there's a full quantity of pollution, then we're collecting tax value T on all 10 units of pollution. So from 0 units of abatement all the way to 10 units of abatement, from 0 units of pollution all the way to 10 units of pollution, we're collecting this full value in tax revenue. When we allow firms to abate, when we allow them to reduce their pollution, then the total quantity of units which they choose to pollute is not going to be that full 10. We can see here that the total amount of pollution that they would produce would be 6. And so we're multiplying 6 by T, and that's going to be our, it's kind of like a G. And that's going to be our tax revenue. And our total tax revenue is then the smaller yellow square, I need to watch my Sesame Street, and the total abatement cost is going to be the area underneath the abatement cost curve for the total units abated, which is going to be 4. So this graph also illustrates how the total cost to the firm, to the polluting party, is going to be reduced when they have that choice to abate and to reduce their pollution rather than just fully pollute and pay a tax on that pollution. And so they are saving this white triangle above the total abatement cost curve that they would otherwise be paying in the form of a tax. And we can then use this framework to think about differences in firms based on their costs of abatement and how that will then lead them to choose to reduce their pollution to different levels. So let's consider 2 firms, one with a relatively high cost of abatement, being this firm 1. And so for each unit of abatement, they are needing to pay more to further reduce their pollution per unit. That marginal cost increases. And for firm 2, the marginal cost increases as well, but at a slower rate. And so firm 1 is going to choose to produce A1 units of abatement, meaning that they're going to pay taxes on everything below and to the right of that intersection. Firm 2 is going to pay taxes on everything to the right and below of the intersection of their marginal abatement cost curve with the tax curve. So it's just going to be the smaller blue square. And remember that they have to pay the abatement cost underneath the abatement cost curve for every unit which they abate. However, they, by not abating the same number of units as firm 1, by not abating A1 units, instead by abating A2 units, they're going to have this additional savings which firm 1 is paying in taxes, and firm 2 can avoid paying that in taxes by abating more than firm 1 abates. And so there's going to be differences in the optimal level of abatement depending on the abatement cost curves for those firms. And so why do economists like price-based instruments more than command and control type approaches? Well, the price mechanism is going to create incentives for firms to use cleaner technologies, and they're going to choose to invest in those technologies to abate below that command and control level if it's cost effective for them to do so. And so they're going to try to find alternatives where their marginal abatement cost curve is lower than the tax rate instead of paying that tax. And this is going to be able to create the right price for the tax, for abatement, and for exchange of abatement permits between firms rather than just imposing a quantity through a command and control type approach, because it's going to allow firms to use the knowledge they have about their own marginal cost curves to find the lowest cost opportunities. And so we can also use trial and error as a way to figure out the right emissions level, the right level of the emissions fee, which may be harder to do with a command and control approach because firms aren't going to be responding on the margin in such a capacity. So using what we now know about price-based instruments for pollution control, let's apply this taxation or fees on emissions rather than on products approach to thinking about cap and trade and markets for tradable permits. And so this used to be a pretty popular way among those who are more conservative in their political alignment to support climate change policy. And it seemed to go out of fashion maybe around 2010 when the Tea Party came into power, and probably people just got wind that cap and trade is essentially the same thing as a tax. But just the word trade being in the title gave it a little bit more support among conservative politicians and economists than the tax, even though, as we'll see later this class or maybe next class, they achieved the same level of reduction through government intervention. So cap and trade is going to have some components of a quantity-based approach, of a command and control type approach, and some components of a price-based instrument as well. And so we're going to think of cap and trade as being the process of assigning a fixed quantity of permits, which must be purchased or traded for each unit of pollution released. And each firm will be allocated permits either by lottery, by being assigned them or purchasing them, which then they can trade with other firms. So let's consider just a simple example about how this permit trading would work. And remember what we discussed at the beginning of this video, that if firms were completely unregulated, if polluting companies were just left to their own devices to make profit maximizing decisions, how much would they choose to abate? They would choose to abate zero, meaning that they would have this full level of pollution and 0 units of abatement. So let's assume that full pollution looks like 12 units of pollution that they would each be capable of producing if they were unregulated. Now suppose the government wants to set a goal to reduce total pollution by 50%. So instead of each firm producing 12 units of pollution, they're only going to be permitted to pollute 6 units of pollution each. And so you must abate the 6 units which you are not permitted to pollute. So that's where the command and control approach kind of comes in, that there is a limit on how much you can pollute, and you're not allowed to pollute more than the permits which you have. So because these firms have different marginal abatement costs, this is going to imply room for trade and improvement in their profit margins by taking advantage of those difference in abatement costs. So let's work our way through this iteratively to see how they could trade with each other to have a more efficient outcome. So when both firms have 6 permits, which are assigned to them by the government, the marginal cost of abatement for that very next unit of abatement for firm 1 would be 3. And the marginal cost of abatement for that very next unit of abatement, which firm 2 would need to produce, would be 1.5. And so remember, if you don't have a permit, you have to abate. And so since they produce 12 units of pollution and they have 6 permits, then they have to abate 6 units, and the marginal cost of that 6th unit of abatement is going to be 3 for firm 1, 1.5 for firm 2. And so firm 1 would be willing to pay anything less than $3 to buy a permit to abate, a permit that would allow them to pollute instead of abate. Firm 2 would be willing to accept anything more than $1.5 to abate, rather than just abate on their own. So firm 2 could say, okay, it's not going to be too costly. I could choose, after my 6th permit, I could choose to reduce pollution on my own. It's going to cost me $1.5 to do that. But if somebody's willing to pay me $2 for one of my permits, then I'm willing to abate even more than I already am, because you are more than compensating me for my efforts to further abate relative to what I already need to do. So if they trade one permit and firm 1 pays firm 2 somewhere between $3 and $1.50 for that permit, then firm 2 only has 5 permits, meaning that they need to abate 7 units of pollution. Firm 1 has 7 permits, meaning they only need to abate 5. They are permitted to pollute 7 units, and they have to abate 5 units. And we still have a difference in their marginal cost of abatement. So now firm 1 would be willing to pay $2.50 for one more permit, and firm 2 would be willing to accept $1.75 to sell a permit and choose to abate more. So there's still room for trade. And if they engage in trade, then they trade 2 permits, then firm 1 is going to abate 4 units because they have 8 permits, so that equals their total 12 units of pollution. So they are permitted to pollute 8 units because they have 8 permits, and they have to abate those extra 4. And the marginal cost of abatement for that 4th unit of pollution is going to be $2. Firm 2, on the other hand, only has 4 permits, so they're only permitted to pollute 4 units, and means they're going to have to abate 8 units of pollution. And the marginal cost of abatement for that 8th unit of pollution is going to be $2. So the marginal cost of abatement for these firms are equal, and the total number of permits that are out in circulation between these 2 firms is equal to 12. To 12. And the total amount of emission that's going to be reduced through abatement is going to be equal to 12 as well, still cut in half. What happens if they trade a little bit more? Well, now the marginal abatement costs of firm 2 are actually higher than that of firm 1. They would prefer to not abate more, and they sold too many of their abatement units, and they'd be better off buying a permit back from firm 1 for somewhere less than $2.25 and above $1.50, and they'd be made better off. So from start to finish, looking at the initial point of both firms with 6 permits and an abatement cost of $1.50 on the margin for firm 2, an abatement cost of $3 on the margin for firm 1, if they sell 2 permits, or if they exchange 2 permits for a price between $1.50 and $3, then we know by the second equimarginal principle that we're going to have an efficient reduction of pollution. And so by setting the marginal abatement cost for firm 1 equal to the marginal abatement cost for firm 2 for the optimal solution, for completely maximizing gains from trade, then firm 1 produces 4 units of abatement, firm 2 produces 8 units of abatement. And we can see these interesting little triangles here that are catty-corner, and think about how they represent the gains from trade. So it's important to note that the permit costs wash out, that firm 1 buys permits from firm 2, but how much money firm 1 loses in terms of what they pay for the permits is exactly equaled by how much firm 2 gains. And so the total benefits it's just a transfer. There's not any new value generated. The value comes from the savings in underneath the marginal abatement cost for firm 1 and the benefit to firm 2 of being paid to abate more. And so we could illustrate this by thinking about what the total cost of firm 1 would have been. And do that in purple. So everything under the marginal abatement cost for the number of pollutants that they would needed to have polluted. And now they only are going to incur the costs underneath the curve. I'll use a different color purple here. For the 4th unit. And so they save everything in this blue trapezoid, but they pay everything in this green square. So they're buying 2 permits from firm 1 at a price of $2 a permit. So 2 permits at $2 a permit. It's just going to be 2 times 2. It's going to be this green square. And the only part of that blue that's left is going to be the little blue triangle above the green rectangle. Now that green square is just being transferred directly to firm 2. And so it's just going over here. And so even though firm 2 has additional abatement costs of this red trapezoid, there's this little green triangle above it, which is the payment that they got for abatement from, for additional abatement from firm 1. And so hopefully you can see where those gains from trade come from. And going back to Econ 101, we're thinking of trade as a technology that creates value here. So hopefully it's a little more clear now why we prefer cap and trade over a command and control type approach. First of all, it's going to fix the missing market problem by creating a market for pollution. Remember, we thought that was part of one of the types of market failures which lead to inefficient environmental economic outcomes. Otherwise, pollution itself doesn't have an explicit market. It's going to be good at transmitting information about costs through the negotiation between firms for permits. It's going to be incentive compatible for firms to reveal information about their true cost of abatement because they can then negotiate more accurate they can acquire permits at a price which is going to be more beneficial for their. Sorry, I've got my baby monitor right next to me, and baby just spoke up. For profit maximization. And so importantly also, it also creates the incentive for dynamic efficiency and technological improvement to reduce their marginal abatement cost curve, which would then decrease the total cost of abatement which they would need for all units of pollution for which they do not have a permit. However, this isn't the end all be all. It's not the panacea or manna from heaven solution to reducing pollution. There's still a question of how we allocate permits, that if we allocate them equally across firms, then this may not have the efficient solution if we think of the endowment effect of people not wanting to trade, or it may not be equitable to do so if it's based on previous emissions, in which case we're grandfathering in some permits. And I put grandfathering here in quotation marks because a lot of, this is a really common phrase in policy, but just so you all know, this phrase does have a history in racialized systems of prejudice in the United States, in allowing as a way to disenfranchise Black voters and allow poor and illiterate whites to continue to vote after Blacks were originally franchised, by saying that if their grandfather voted, at which point in time only white people could vote, then they could continue to vote. So it was, it's really unfortunate that this phrase is still continued to be used in policy making, but I thought this was a teachable moment to bring up that fact. And we could also allocate permits by auctioning. And so we've got three different ways that we could allocate them. There's going to be different efficiency and equity concerns. And it's still going to require us to have some information about what the optimal level of emissions would be, which is that fundamentally difficult task of gathering information about the marginal social benefit and marginal social cost of pollution in the environment. And similarly here, firms have transaction costs. There are always frictions in exchanges, and it's going to require administration costs by the government to monitor that market. So again, it's not a panacea, but it's really one of the more efficient solutions that we have. But it's going to give us the exact same solution or outcome as taxes will, when there is absolute certainty about the marginal cost curve. And when there is uncertainty about marginal cost curve, then the efficient solution may depend on the relative slopes of the curves, which is going to imply using, referencing our old friend Marty Weitzman, which we discussed back in week 2, and using the Weitzman rule as a way to think about whether taxes or quotas will be more efficient. And that we are going to talk about next week in class.